So welcome everybody to today's AJS seminar. Today we have Davide Torlo, and he will talk to us about arbitrary high order positive preserving time integration with application of shallow water equations.
Thanks, Francesco, for the introduction, and thank you all for being here today. And as he said, I will talk about some hints which try to preserve the positivity of the solution. And in particular, we try to do this in an accurate way. In particular, we need to get high order schemes in order to be very accurate. And we focus on arbitrary high order schemes in order to be as accurate as we want with our methods. And finally, we show some application for shallow water equations. And here you can see that when you want to simulate the water equations, you want to have the positivity of the water height. And that's why it's important to have this type of schemes for this type of applications. This work is in collaboration with Mirko Cialella in Ivrea Bordeaux, Lorenzo Michalizzi at the University of Zurich, and Filippo at the University of Mainz. So let me start summarizing the table of contents. So first of all, I will describe production instruction systems, which are some ODEs which can be written in a specific way. And this type of systems preserve the positivity of the constituents. And there are many applications that can be written in this formulation. Then we see the fair correction time integration methods, which are high order, arbitrary high order time integration methods, and the modified pattern calculation, which are some positivity preserving, unconditional positivity preserving modification of the fair correction method. And then we see some of these tests. Then we see how to apply this also for shallow water equations with a finite volume schema. So in particular, the difficult part, I mean, the thing that will be a bit tricky is to write the finite volume scheme as a production instruction system so that we can apply the modified pattern deck for this. And then we see some simulation. So let me start from production instruction systems. So what are production instruction systems? Are some of these that can be written like this. CI are our constituents that we want to know. And this is derivative in time. And they evolve as some production, PI, minus some destruction, DI. These production and destruction terms are both of them positive. And they can be written as some contribution, PIJ, DIJ, where PIJ is the contribution to the constituent CI coming from the constituent CJ. So in particular, if I have a PIJ, it means that some production, some mass will move from the constituent J to the constituent I, while the destruction will be the opposite. So in particular, all these terms must be positive in order so that we know which mass transfer is going in which direction. And there are some properties that can be proven on this type of models. So for example, conservation of the total mass. This is given if and only if these production and destructions are essentially one the transpose of the other one. So if I produce something from the constituent J to the constituent I, this is actually a destruction for the constituent J coming from the constituent I. So there is this symmetry. The positivity of these systems is given if we have these properties. So the production instruction should be Lipschitz continuous, and if the constituent is going to 0, also the destruction is going to 0. This allows to prove the positivity of the solution at any time. So if we start with some positive constituents, this will be positive always in time. Why is this important? You can imagine for chemical reactions or biological system, population evolution, we have this type of properties. Usually there are some chemical reactions which transform some materials in something else, or some population which evolves. So these days it was very famous, the SEER model for simulating COVID. You have different population with changes, and there is always some production going from one side to the other one. So for example, from one class to the other one. And also some other PDEs can be written in this framework. And we will see some example later. So now let's try to approximate the solution of these systems. Since we cannot always have an analytical solution of this system, we want to approximate them in an accurate way. So the first possibility to discretize this scheme is the simplest explicit Euler method. So let me summarize what it is. It's CIN equal to CIN, CIN plus 1 equal to CIN plus dt times the sum of the production terms minus the destruction terms, evaluating Now, this scheme is very simple, is conservative, as if we sum over all the constituents, the Pij are the transpose of the Dij, so this cancel out. This scheme is only first order, and it is also positive if dt is small enough. So if we choose a very small time step, depending according to the production and destruction, we can be positive also with this kind of scheme. And of course, it's an explicit scheme. Now, what we would like to have is something which is a bit more safe in a certain sense, because we don't want to put restriction on dt in order to be positive. So what we can do is to use, for example, implicit order. Implicit order will be positive. What is happening, essentially, we evaluate Pij and Dij in the implicit state, so Cn plus 1, and this is probably positive. Problem, we don't know Cin plus 1 a priori, so we will need some nonlinear solver in order to solve this equation. And in the hyperbolic community, people don't like so much implicit schemes and nonlinear solvers. We prefer explicit stuff. So in order to solve this, you need something. This can be a very complicated system at the end of the story. So it might be complicated also to find the zero of this equation. So we don't really like so much this type of discretizations. And moreover, if we want to go higher order, there are theorems that say that only first order implicit Runge-Kutta schemes can be positivity preserving. As soon as you get second order, you cannot be unconditionally positive anymore. You still need some restriction on the time step. So if you want to go higher order accuracy, higher order accurate, and being unconditionally positive, we have to invent something else. In 1980, Patanka changed the explicit order method, so here we have Cn, with this weight. This weight is a simple fraction between Cin plus 1 and Cin, which was put in front of the destruction terms. And this makes the scheme implicit, but not, it's linearly implicit. It's even very simple here to solve because we can collect the Cin plus 1 term here on the left. And we can see that here we obtain something which is 1 plus the sum of the destruction terms divided by Cin, which is something positive. All these terms are positive, equal to times Cin plus 1 equal to Cin plus the production terms. And all these terms are also positive. So Cin plus 1 is simply the ratio between these two terms, which are positive, and it's again a positive quantity. So with this simple trick, what you get is a scheme which is unconditionally positive for any delta t. This will be positive. It's almost explicit, it's implicit, but it's very simple to solve. We don't need any nonlinear solver. And again, it's only first order accurate because we are just looking at Euler with a small modification, which is an O delta t square essentially. So it's not changing the order of the scheme. And the problem is that it's not conservative. So what you've seen before, that the production and the destruction cancel out somehow because one are the transpose of the other when you sum up all the constituents. Putting this weight, essentially, you don't have any more dissymmetry.
Sorry, what is done on the destruction?
Because the destruction are the negative part. So you want to avoid to have something negative on the right-hand side in order not to go below 0. So in this way, putting this weight on the destruction, you essentially move this part on the left-hand side, and it goes on the diagonal term, let's say. So it's a positive coefficient, and then everything is positive. And yes, so the problem with this scheme is that it's not conservative because we have these weights only in the destruction terms. So in 2003, they added the weight also on the production term. In this way, you restore the conservation. So the difference between these two terms is that here we have the Cj weights and here we have the Ci terms. What does it mean in practice is that this term will not go in the diagonal term of this left-hand side, but it will go on the off-diagonal terms of a mass matrix that will be created here. So what we have is just a linear implicit scheme because the Cin plus 1 are always linearly depending on some constituents which are explicit. And what we say is this mass matrix times Cin plus 1 equal to Cin. So the clue of this mass matrix is that on the diagonal terms, you have what we've seen before for the Patanka Euler, so 1 plus the sum of the destruction terms, which is positive. And on the off-diagonal terms, we have minus the production terms divided by Cj, which are coming from this term. Now, we will see later that if Cn is positive, we can prove that this system has a positive solution as well. So Cn plus 1 will be positive as well. So the difference between the previous scheme is that we are conservative this time. Again, we are only for solar accurate, and we are still unconditionally positive. We can prove that this matrix will give a positive solution whatever time step we choose. On the other side, we have a linear implicit scheme, so we need to solve this system at a certain point, which is not too bad. It's not an explicit scheme, but it's not also a non-linear implicit scheme. So it's a good compromise. Later on, so starting from that paper, there were a couple of more papers describing some Runge-Kutta modification of this scheme, where essentially we went to up to second and third order. Essentially, you have to put here the Runge-Kutta weights, you change some states in order to be consistent with the order of accuracy, but the process is more or less the same. At the end, you have a mass matrix for every stage of the Runge-Kutta scheme, where you have a positive part in the diagonal and the negative part in the diagonal terms, and you get higher order of accuracy. And in 2020, we also did the arbitrary high order version of this scheme, based on the defect correction that we will see later in details, so that we are arbitrary high order, also unconditionally positive, arbitrary order, and conservative. The only price we have to pay with respect to an explicit method is that we have this linear implicit system, so we need to solve some linear systems every stage in this process. Now, let me show you why this system gives a positive solution. So let's consider the Tatanka or modified Tatanka-Euler system, so the simplest one for all the Runge-Kutta, and the proof is the same. We have Cn, which is positive, and we have the mass matrix, which is composed of some terms on the diagonal one, which is 1 plus the sum of the distractions. And on the off-diagonal terms, we have the production terms with the minus in front of them. So we can write M as a diagonal matrix, which is maybe this diagonal part, minus A, which is all the off-diagonal terms, essentially. And all these terms of D and A are positive or non-negative. What we can prove is that M is diagonally dominant by columns, because DII is strictly bigger than AJI summing over J, because all the distractions are the transpose of the productions, so these terms cancel out when you sum over all the production, and there is an extra one here, so the diagonal is always strictly bigger than the sum over a column of all the terms. So since this matrix is diagonally dominant by column, we know that the Jacobi iteration will converge. Now, the Jacobi iteration method for the solution of this system is straightforwardly written in this way. So xp plus 1 is equal to b minus 1 axp plus b, and all these terms are positive. B is the right-hand side, so we start from a positive or negative previous step. Xp, I mean, it's iteratively positive. We can choose initial guess anywhere it is positive. A is a positive matrix. D is a positive matrix. So all these terms will be positive. This sequence of vectors will converge towards the solution of the system. So the solution of the system will be positive as well. This is a very straightforward way to prove that the solution of the system of all these modified Tatanka methods will be positive. Let's go high order, arbitrary high order. The defect correction method is a one-step method, like the Runge-Kutta methods, which allows to create very easily arbitrary high order methods. Explicit in particular in this case, but also there are also implicit versions. We will focus on the explicit one. So let's consider the interval Tn plus 1, and we want to go from the known value Cn to the unknown value Cn plus 1. So what we do, we divide the interval into sub-time intervals, T0, T1, Tm, Tbm, and we discretize also our unknown here in C0, C1, Cm, Cbm. The idea is to mimic the Picard-Lindelof theorem and to approximate the integral value of the ODE from the interval T0 to each interval Tm. So we can write Cm as C0 plus the integral from T0 to Tm of the evolution operator, P minus D. Now, according to how many points you choose and how they are distributed, you can get an arbitrary order method, and we will see soon how. So let me consider this C underscore as the vector of all these components over the certain intervals. We now construct two operators in order to get these high order methods. So the first is an high order operator, the L2 operator, which is the final list. So this is exactly the formula that we've seen before. For each interval C1, C0, Cm, C0, we write Cm minus C0 minus the integral from T0 to Tm of the evolution operator, we don't see. And we can write this with an high order quadrature formula here, so we get some coefficients where the quadrature points are the same points when we discretize the interval. So that these CR are essentially the same C1, Cm that we have here. And if we put this operator equal to 0, what we get is essentially an implicit Ungefutta, which is high order, but it's an implicit Ungefutta. So it's difficult to solve directly. You will have some nonlinear terms. So we don't really want to solve this. We would like to have the accuracy of this L2 equal to 0 scheme, but we don't want to solve it directly. The defer correction method introduces another operator, L1 operator, which is a simplification of this L2 operator. It takes the same form, but instead of using an high order quadrature formula here, it simply considers explicit Euler method essentially. So we just integrate with E at the values which is known, the C0 at the beginning of the time step. And we define these two operators. So this L1 operator, if put equal to 0, gives a first order method, which is simply the explicit order method, but it's very easy to solve. So what we can do is to combine these two operators in order to get an high order accurate method, which is explicit. So we have this vector of C0, C1, Cm, and what we will do is to do some iterations, which we denoted by this index k, in order to get an high order approximation of this vector of unknowns. In particular, at each iteration, we gain one order of accuracy. How do we do this? So, first of all, we define the initial time steps, the initial iteration and the initial time steps defined as the previous time steps. So Ctn will be the one which defines this side and this one essentially. And then iteratively, we define the following the k+1 iteration of the k iterations as the solution of this system L1 of Ck equal to L1 of Ck minus 1 minus L2 of Ck minus 1. So L1 is a simple operator, it's explicit, we can solve it directly, even if we put some right hand side, it's fine. And these Ck minus 1 are already known from the previous iteration, so we just plug in this solution inside these two operators. Now, if L1 is cohesive, L1 minus L2 is which is continuously constant, delta t times some constant, then we can prove that this iteration process is high order accurate, and in particular, at each iteration, as I was telling before, we gain one order of accuracy until we reach the accuracy of the L2 operator. Then after that, we are more or less done. So if you choose, for example, L2 operator and where it is fifth order accurate, after 5 iterations of this process, you will get the fifth order accurate method. Now let me show more in concrete what is this scheme. So let's focus on one substance step M and one iteration K, and let's see what does this formula mean. So the L1 operator is simply Euler, explicit Euler, so Ci Km minus C0 minus T, the explicit evolution operator, equal to the previous iteration, so Ci K minus 1m, this is already known, minus C0 minus the same term, minus the L2 operator applied to the previous iteration, so this is already known. We have this term again, plus the sum of the high quadrature formula, time, but we have all the previously computed Ck minus 1 R terms, which gives the high order accuracy. So if we simplify all the color terms, so green and green goes away, blue and red, we get this formula. So in particular for this is the kind of formula that you get for this type of defer correction schemes. And what we can see is that everything is more or less inside this yellow part. So the crucial part is what is defining the Del2 operator. Okay, now this is a method to get an high order explicit arbitrary high order time integration method. What we would like to have is something which is, as I told before, positive preserving with the Patanka trick. So what we have to do is to insert some weights in front of this coefficient. So what we will do is to modify the L2 operator in order to have the same properties of the Patanka methods that we've seen before. So let me summarize again what we want to do. We want to use the deck because it's high order operator. We want to preserve the positivity and the conservation. So we will use the Patanka trick that we've seen before. And we will have something which is linear implicit, not implicit and not anymore explicit. It's easy to solve. And we just modify the L2 operator to get this, this modification. How can we modify this L2 operator? So this is again the L2 operator. So we have the high power 2 formula. I explicitly written here the production and destruction terms because now we have to weight them as before. So the destruction are weighted by CI divided by CI, and this is given is the implicit term CIMK, while this is an explicit one CIMK-1. And here we have the CJ, so the off-diagonal terms. So with this simple trick, what we get is again a linear system that you need to solve, and we are positive almost. One problem is that this theta coefficient, the high quadrature formula that you have in time, might be negative. So what we have to do is to switch J and I when this coefficient is negative, and this can be written in this way. And essentially, this switches the production and destruction terms from the diagonal and the off-diagonal terms when theta is negative. It's just a technical thing which makes everything positive, but it's essentially the same trick of the modified Patanka schemes as you see before. Now we can simplify again the L1 minus L1 plus L2 formula, and we get these schemes that, as you've seen before, is I mean, we can prove that it's conservative, it's positive preserving, and high order accurate. Let me quickly show why it is conservative. As we've seen before, the productions here are the transposition of the destruction, so I can write as dji here. But since we want to sum over all the constituents, the I and j can be inverted because they're summing on both of them. So this dji becomes dij, and this term is exactly this one, so this is equal to 0. Positivity is exactly the same thing that you've seen before. In the simplified version, but the properties of the matrix are the same. And finally, high order accurate, because we can prove the same modification of the theorem that you've seen before. Essentially, you still need that L2 must have a solution, C star, and L1 must be coercive in this sense, and L1 minus L2 should be Lipschitz continuous in this sense. So the sense of this Lipschitz continuity and coercivity have changed a little bit, but they can be easily improved for the operators that we define. And then we can prove that at each iteration, essentially the error between CK and the solution of the two operator is smaller than dt times the previous error at the previous iteration. So we gain one order of accuracy at each iteration. And this gives the high order accuracy of the whole method. This is the method that we will use. And let's see some tests for ODEs. This is a linear test. We have two constituents, C1 and C2. And this is the solution, more or less. This is second order and the fifth order method, nothing special. The order of accuracy is the expected one, second, third, fourth, fifth, sixth order methods. And so here the order is reaching more or less the order that you expect. And on linear test, it is a bit more challenging. There are three constituents and there is a bit more going on. There are some nonlinear terms, and here we can see there are some stiff terms. Here we go very, very, very close to 0, but we never hit 0. And here the conservation of the quantities is guaranteed. I can see that this line, you can see it. You can see again the accuracy, and again, second, third, fourth, fifth, sixth order, everything looks fine. Finally, a more challenging test, which is the Robertson test, where we have very different scales between these two constituents and different reactions. So we can see that there is something like 10 to the power of 4, 10 to the power of 7, and 0.04. These reactions are very different in time scales, and it is very challenging to be taught by usual schemes, explicit schemes, but also implicit schemes. And we see that we don't have problems with these pattern schemes. The positivity is always guaranteed, and the conservation of the constituents. And essentially, you can see the time scale varies a lot here. So we start with very, very small times, and then we have to increase the time step in order to get to these very long reactions, which takes a lot of time, needs a lot of time to occur. Let's change a bit the goal, in the sense that we want to study new applications, in particular shallow water equations. So what are shallow water equations? They can be written as some balanced laws, where we have the derivative in time of some unknown u, where u is the vector of unknown, which is h, the water height, h times u, where u is the velocity in the x direction, and hv, where v is the velocity in the y direction. Then we have b, the bathymetry, which is a datum, which is the bed of your river, of the ocean, whatever it is. And eta is the sum of b and h. Now, the equation is written like derivative in time of u plus the divergence of the flux f equal to a source term. And here we can see that in the flux, we have some terms which comes from the conservation of mass and momentum, and some gravity terms. And in the source, we take care of the contribution of the bathymetry. And what we would like to do, again, is to solve this equation with some, a very accurate numerical method, in a way that the solution is positivity is, the water height must be always positive, in particular because when you have this type of simulations, you're often interested in some quantities like the square root of g times h that you need to calculate the speed of propagation of the waves. So you want h to be positive, otherwise you will end up with some not numbers in the code. So it's important that h stays positive all around the domain. So we want the scheme to be positively preserving. We want the scheme to be very accurate in the sense high order discretization in space and time. And in particular in space, we will use a finite volume discretization with Wiener reconstruction. We will see some details later. And we want to conserve total mass and also some particular states. We want to conserve them at machine precision, like this one where you have zero velocity, eta is constant. And when the bathymetry is not constant, this is not trivially conserved by all the numerical methods. So this is something that we would like to add as a constraint to your method. Now let's review quickly the finite volume method. So we want to discretize our unknowns as on a Cartesian grid. So we take this omega I cell and we take uij as the average value over the cell of our unknowns u, and these will be the quantities that we evolve in time. Then the fluxes must be discretized in this way, and the source as well. In particular, the source will be the integral over this cell again of the source term, and it will be computed with some high order product formula. The fluxes will be discretized on the edges, so we can see what quantities come in from the other cells and what is going out. And again, since we need to compute the flux along this edge, and we have considered the solution to be, we know the solution at the average on the left side, and on the left side, we know the average of the solution here. So it might be that the construction here at the interface is not continuous. So in order to take care of this flux, which is here discontinuous, we will need some numerical flux. And for example, here's the reasonable flux, which takes care of the wind of the problem. So it transports the information in the right direction. And then we integrate over the edges with some high order product formula in order to maintain the accuracy of the scheme. Now, in order to get an high order reconstruction, so we know the cell averages, and we would like to have an high order reconstruction, for example, in the quadrature points of the cell or on the edge of our cell in order to compute the flux. We will use the weighted, essentially non-oscillatory reconstruction, which in few words does this. So let's consider the Wien-5 fifth order reconstruction method. We want to reconstruct the solution inside the cell I, and we have these 5 information, so the cell averages at these 5 neighboring cells of the cell UI. Wiener reconstruction considers one high order polynomials, which essentially fulfill the 5 cell averages quantity that you've seen before, and 3 low order polynomials, which are defined on different stances. So the P0 is only defined from here to here, P1 from here to here, and P2 from here to here. The Wiener algorithm essentially searches for some optimal weights in order to get the highest possible reconstructions, and then it weights again these optimal weights with some smoothness indicator in order to move back to the less oscillatory polynomials in case there are some oscillations. To do so, for example, it fixes in different points, for example, the interface points or in partial points. It finds these optimal weights DJI, which are essentially the solution of the system for host points. So you find these coefficients, and then given some smoothness indicator of these 3 polynomials, you can decide which polynomials you want to weight more or less. In case one polynomial is oscillatory, you essentially discard that one and take the other 2. And this decreases the order of accuracy, but gives stability to the scheme. Now, this reconstruction might not be positive, even if all the cell averages are positive. So what has been done in the past is to use this positivity limiter, which is written in this way. It's not too complicated. I mean, you can write it in one slide, so it's easy, but not also super trivial. What is important here is that it depends on one minimum value that you want to allow as the minimum value in the cells. And it depends on these Gauss-Lobato weights, which should match the order of accuracy you want to have in your method. So what is nice of this positivity limiter is that it's probably positive. So we know that the scheme will give this limiter will give a positive reconstruction. It's very local in cell. It's very easy to implement. It's explicit. Problems, it relies on these Gauss-Lobato weights. In particular, so these Gauss-Lobato weights depends on the order of accuracy. For example, for Wiener 3, it's 1/6. For Wiener 5, it's 1/12, and so on. And it also constrains your time step. So what does it mean? So the CFL constraints are usually some restriction on the time step that you use for explicit methods in order not to violate physics. So you want all the ways to move at most of one cell inside during the scheme. So what you do usually is to take dt smaller than CFL times the spatial discretization. What you need to do here in order to guarantee the positivity is to decrease this CFL by a factor which is given by this Gauss-Lobato weight. So, for example, for Wiener 5, we would have to run this scheme with a time step which is 12 times smaller than the original one. So this means that we have to run 12 times. I mean, the computational cost of the code will be 12 times longer. So this is a problem. We would like to avoid to have this constraint. Moreover, the proof on this positivity limiter relies on explicit order methods and can be extended to strong stability semi-Lunge-Kutta methods, which are convex combination of explicit order steps. Another problem is that these strong stability semi-Lunge-Kutta methods, if you use positive coefficients, can be at most order 4. So we cannot have arbitrary order accuracy. So even if you use Wiener 5, you have to stop with order 4, which is a bit. I mean, why do we use such a high order reconstruction space if you cannot go higher order in time? So what we would like to do is to improve these problems that we have, these issues that we have, this positivity limiter, using the modified pattern that we have seen before, which is provably unconditionally positive. So we don't need to impose any CFL restriction to maintain the positivity of our solution. This is the other technique which I will not describe today. Essentially, if you want to obtain some well-balanced when you have some steady states where, for example, in the lake at rest, everything is flat and there is no velocity, you might want to use some techniques here. For example, it's a very simple technique. You just subtract whatever you have for the analytical solution, and then you plug this inside the code, and you get very nice results. I will show you some results, but it's not really the focus of today. And let's see what we finally want. It's these finite volume schemes with Wiener reconstruction, and we want to make them arbitrary order also in time, and we want them to be provably positive. and without the CFL restriction that you've seen before with 1/12, something like that. You want to run a CFL1. Moreover, we would like also to apply the same technique for the well balance states that you've seen before, but it's a plus, this part. Now, what can we do? So we've seen a finite volume scheme and the production instruction systems. How can we write a finite volume scheme as a production instruction system? So let's focus again on these terms. So in particular for the water height equation, we don't have the source term, so there is only these fluxes going out and in from each cell. And we can see that these fluxes are somehow some production and destruction terms. So if we focus, for example, on the first one here, f I minus 1/2 j, we can see that this, if it is positive, this is essentially a production for the cell omega ij coming from the cell omega minus 1 j. So we can simply define the production for this system with all our unknowns as the positive part of this flux. And if it is negative, then this is the destruction for the cell omega ij with respect to the cell omega minus 1 j. So we simply consider the destruction to be defined like this. In this way, we can assemble a production destruction system after we did all the finite volume discretization. We simply define these production destruction terms, and then we apply all the schemes that we see for the modified for the production instruction system. All the modified parameter schemes can be applied directly to this production instruction system. So, summarizing the steps that we need to do to put everything together. The well balanced technique, we can do it or not. It's just a simple step that one can do at the beginning. Then we do the Wiener reconstruction with the positivity limiter that we've seen. We assemble all the finite volume fluxes. We build the production and destruction terms, and we build the mass matrix at every iteration of the Runge-Kutta or the modified Tatanka-Deck scheme that we've seen. We saw the linear system, and I tell you that I was lazy, and so you didn't implement anything fancy. It's a Fortran code, very, very basic. I used Jacob iteration, what you've seen before, to prove the thing. It's exactly what is in the code, and it's anyway very fast, and it's like a 10% more of the computational. I mean, it's the time of the inversion of the system is more or less the 10% of the code, so it's of the computational cost of the code. So it's not very expensive, since the matrices are very sparse, and also the number of iterations that you need to reach the convergence is very low. And finally, we update. So with the modified Tatanka deck, the water height that you want to be positive, and with the classical deck, we evolve the other quantities. So it's still an explicit scheme for the other quantities, while it stays implicit for the water height. So in this way, what you obtain is a scheme which is unconditionally positive, arbitrary high order in space and time. You can use a high order reconstruction window and arbitrary order deck, it's not a problem. There is a small difference with respect to the classical finite volume scheme, because we just studied this production and destruction framework. So you take already your fluxes, whatever is already there, you just write them as production destruction part, and then you send this, and you change the time in discretization. We can improve the CFL from 1/12, from like, for example, 1/12, the one of Wino 5 to 1. And why 1 and not more? We are still explicit in the other components, so we cannot go with arbitrary time step. We still need to constrain the time step for the physics for the explicit part. And the price that you have to pay is this little extra cost, which is around 10% of the whole computational cost for the solution of this linear system. Now we show you some results which we obtained with Wino 5. So we focus on fifth order schemes with the Rosen numerical flux, CFL more or less over 0.9, and we say Tatanka deck again with fifth order, and it can be written like I mean, it's this one with this distribution of points, just details, but it's I mean, if you want to imagine it as a Runge-Kutta scheme, it's a Runge-Kutta with 13 stages. Moreover, we used periodic boundary conditions because we were lazy. Now we implemented also other boundary conditions, but the solution, the simulation that you will see are only periodic boundary conditions. And the well balanced techniques will be done only for the lake at question, when velocity is 0 and the water level is constant. So let's have some simulations. First of all, let's check the order of accuracy. These are some exact solutions. These are moving vortices, and we know the exact solution. plenty of family of these vortices. We can see that with and without the modified Tatanka technique, we reach the 5th order of accuracy. With another test, this is the lake rest of not well balanced. We can see that the order is again 5, just to be sure that the order is the one which is not obtained. Then this is a wet and dry test, which is normally challenging because you have some areas which are dry, so H is 0 or very, very close to 0, and some areas where there is actual physics happening. So we want to see, we want your code not to break close to the interface, essentially. So the bathymetry is this island that you see here on the bottom, and there is the water level, which is 0.7. So it cuts the island here. So inside this island, everything is dry, and outside the island, it's wet. And we have this little perturbation here on the top left of the island, which is a bump of water here. And we let this evolve in time. So there are these techniques, the well balance and the not well balance technique. The not well balance is not very nice because there are some spurious noise coming from the bathymetry. With the well balance technique, we don't see this. There is only the perturbation moving from the original side of the drop towards the island in all the other directions. And these very nice structures are what we expect, while here there is a lot of noise. It's not really the point. What is important that nothing breaks. I mean, we have this dry island and something wet, and everything works fine. So even with H equal almost to 0, this is something like 10 to the minus 7, I remember well, everything worked pretty fine. This is another test case where we have something dry outside and wet here. So here the water height is 2.5 and here is 10 to the minus 6. And then we let this evolve in time and we don't have any problems. This creates a rarefaction wave between these two states. Then this is a wet done break, so the same test as before, but here is not, outside is not 0, the water height, but 0.5, and inside is 10. And this creates a shock here, which is perfectly captured by a high order accurate method as expected, and this rarefaction wave. This is the same picture on the contour plots and these some slices. And this is a strange test that I made up, putting all the possible ingredients that I had in mind. So we have the same island that you've seen before. It's dry on the top at the beginning. We have this water with this perturbation here, and the water is moving with the velocity in this direction towards the bottom, essentially. And this creates a lot of effects. So first of all, the water starts to run up on the island. Then here it starts to dry the island in front of it. Then the perturbation splits into waves. One is going up, one is going backward. Then there are some something which reflects on the island, goes backward. Then this wave starts to break, and there is a shock here, essentially, moving in that direction. And also there's a shock here, and then these two at a certain point meets. And there are some vortices in front of it. Here the islands get dry and wet without any problem. It's always like 10 to the minus 6, something like that, but it's not an issue at all. And the simulation is, I mean, the method is very robust. It can run with CFS equal, here it's 0.9, but we run it up to 1.5, it was fine. So it's, I mean, very robust, let's say. Conclude, what I presented to you is, in particular in the second part, the finite volume scheme with Win of 5 reconstruction, with the positivity limiter, which is often used in this context, but we've used the production instruction system framework in order to use the modified pattern back scheme, which is arbitrary high order, unconditionally positive, and conserves all the quantities. This is not a big cost in terms of computational time, since indeed the sparse linear system that it creates is quite easy to invert, and it's actually a gain because we can run at CFL equal to 1 and not anymore at CFL 1/12. So essentially we gain 10 times the speed of the computation. I mean, it's a speed up of 10 times of the simulation cost. Well, but the thing is they can be applied or not. I didn't focus too much on that. If you're interested in other things like positivity preserving or other structure preserving in the schemes, so for example, entropy preserving or entropy dissipative schemes, or stability of this type of methods, and arbitrary order in time, implicit and explicit methods, or other type of equilibria, I'm working on many of these aspects with different projects. And I was also wondering if this can be applied to some model order reduction technique, but I think it's, I mean, we can think about this. I want to thank you all for the attention. You have a question?
It's also like speaker have any question, they can unmute themselves. Maybe we'll start with the curiosity. Can the Windows scheme be applied regionalized to structured meshes?
Yes, there are Windows schemes for structured meshes, and the same procedure works. I mean, the Patanka is just production instruction, so even if you have a triangle, you just choose what is the production instruction and assemble the system, and then it's done. We know there are something for triangles, but it's just more. I mean, we started from a Cartesian grid, so it was easy to test there. It was fun. We didn't explore that, but it's easily doable.
Functions, but not you need to. We'll link them to Davide later. Maybe it's explain Davide again. See you at the next yes.